Hey guys, how's it going? Welcome back for another Year 9 class at Mathspace Academy. My name's Daniel. Let's make a start, okay? So, last week I posed at the beginning of class a challenging question. So, a couple of the people who have been coming to these classes left some feedback. You know, they wanted a challenging question. So, I gave this as a binomial expansion, okay? So it's pretty hard because it uses a lot of the what we've covered previously on indices as well as algebraic binomial expansion. So is anyone able to get the answer before we start? I'll give you guys just like a minute if anyone wants to write their answer in the chat box, and I'll reveal the answer in a moment, okay? So I'm not going to go through the question, okay, because all you have to do is use the FOIL method, right? Multiply those first numbers, those outer numbers, those inner numbers, and then those last numbers, and then just add the results together. But the difficulty in this question is that you have to use indices to, you know, simplify your answer in the end, okay? So I'll give everyone 30 more seconds. Just if you wanted to have a guess, okay, only I'm going to see your guess, all right? I'm only going to see your answer. No one else is going to see the answer. So this was a tricky one, and maybe no one, it is also difficult to write in the chat box, to be honest, when you've got all these indices. And so I'll just reveal the answer now. Okay, yeah, great, Ray. You've given it a shot. So I got this as my answer when I expanded, okay? Yes, I am just having a look. Okay, let me just double check I didn't get anything wrong there. But yeah, I'm pretty sure my answer was right. I checked it before. So I will, Aaron, I will go through that formula in a moment as well. That was the other homework that I asked you to do as well. Yeah, so that was your answer, okay? So feel free to write that down. And if you didn't get the challenging question, but you want to have another go at it, this is the answer. What I'm going to do is I can share my slides with you later, and that way you can have a look at this in your own time, okay? Yes, so yeah, that's correct, Yusuf. Yep, that's exactly the same answer that I got as well. So what I might do is I might just copy Yusuf's answer because he wrote it in the chat box very nicely for me, and I'm going to share it with all of you. And so I'm going to move on from this slide, and if anyone wants to write down that answer to the challenging question, they can, and that way they can maybe go away and try again. All right, good. So I also asked people to find for me the formula. I think it was for the difference of perfect squares. I can't remember if I did that one myself at the end of class last week or if I asked you guys to do it, okay? So when you use binomial expansion for a plus b times a minus b, okay, you should get a squared minus ab plus ba minus b squared. But then what happens is a times b is the same as b times a. So if you're subtracting it and then adding it, it cancels to 0. So then what you should be left with is the a squared minus b squared. So then you can use this as a factorization. You can go the other way around, okay? So when you see the difference of squares, okay, you can factorize to be a plus b times a minus b. All right, so before we go on to Pythagoras' theorem today, I'll just go through an example of this, okay? Actually, no, it's on the same tab. Nope. Nope, I don't want to go to that yet. There we go. Okay, great. So it's here to start off with. This was actually a challenging application of the difference of perfect squares. So I want to go through this one first, okay? So we're looking at x squared minus 4 over 49, which I can actually write as x squared minus 2/7 all squared, okay? So that's the key to completing this question. Seeing that 4/49, I can square 2/7 to get 4/49. And yes, so Yusuf, your answer is correct. Once you use that formula, okay, a squared minus b squared equals a plus b times a minus b, you can simplify this to become, yes, that's correct, Aaron. You can write now x plus 2/7 times x minus 2/7. And then that is now completely factorized, okay? Looking at another application, this is a cool one. I like this one. So use the difference of perfect squares to evaluate 76 squared minus 74 squared, right? So that would be quite tricky to do without factorization, you know, to work out 76 times 76 and then 74 times 74 and then find that difference, okay? So Ray, yes, you're on the right track, and same as you, Aaron, but now you can keep evaluating. You can evaluate those sums of differences, okay? So for everyone else, okay, I can use that formula. Again, I'll write it on the board. A squared minus b squared equals a plus b times a minus b, okay? And so using that formula, I can write this as the sum of 76 and 74 times the difference of 76 and 74, okay? Now, when I add 76 and 74, I get 150. Okay, and then when I find the difference of 76 and 74, I get the answer of 2. So Ray, yes, you've answered it correctly in the chat box, okay? So Ray's written to me that the answer is 300, and so has Yusuf and Aaron, correct? That's because 150 times 2, that is very simple to solve. It's 300. So that's a cool, neat little application of when you have the difference of two squares, that actually by using this formula, you can then calculate this quite quickly without the need of a calculator, without having to do 76 times 76 and 74 times 74. Okay. Before we go on to Pythagoras' theorem, I also asked everyone if they could give me the formula for a plus b all squared. Okay, did anyone manage to find what that was? I know there were some people in the class yesterday already giving me the answer. Sorry, not yesterday, last week. I know there were people at the end of last week's class giving the answer already, but does someone want to give the answer to the sum of a plus b all squared? Yes, so Aaron has shared with me, it is a squared plus 2ab plus b squared. That's correct, and yet Ray has shared that as well. So when you use binomial expansion, the FOIL method, okay, you should get a times a to be a squared plus a times b plus b times a plus b squared. And those ab terms add together to make 2ab. Okay, so you can use this formula to factorize as well. Same with a minus b squared. Did anyone get the answer to this difference of two numbers and then squared? How do you do that? Yeah, that's correct. Yusuf N and Yusuf E and Aaron, correct. It is almost the same, okay? When you use FOIL method, you get a squared and then minus ab minus ba, and then you get minus b times minus b, which becomes positive b squared. So that only real difference is that you're still adding the a squared and the b squared term, but you're subtracting 2ab. Very good for you guys who did that homework, as well as having a go at that challenging question. Okay, so we're going to make a start on Pythagoras' theorem shortly. I'm Daniel O'Kane, and so I'm your Year 9 maths teacher. If there's anyone here joining us for the first time, welcome. Good to have you here. Some housekeeping. So as I always say at the start of the lesson, can't cover everything to do with the topic in 1 hour or in 1 week, okay? But we can do a pretty good job at summarizing it, okay? So today we're going to be starting Pythagoras Theorem, and we'll continue with another lesson on Pythagoras Theorem next week, okay? But I don't expect to go into as much detail as your teacher normally would be able to when they might spend 2 or 3 weeks working on this topic, you know, several hours a week, okay? But we do a pretty good job at summarizing, okay? And so what I do is I follow the Mathspace curriculum, okay? Just out of curiosity, you can show your hands. I think you can raise your hand in Zoom. I don't usually use this feature very much, but maybe a show of hands who actually uses Mathspace, okay? Do you have Mathspace with your class, okay? So show of hands. Oh, actually I've got 9 people raising their hands, and I can see there's 12 students today. So I'm going to guess that 9 of you are using Mathspace and maybe 3 of you not. Possible that the other 3 just haven't raised their hand, okay? So what you could do as a student, okay, if you have access to Mathspace, all right? Yeah, so feel free to lower your hands, that's fine. So you can log into Mathspace and you can come to the topics page, okay? And in your Year 9 curriculum, okay, now I know some of you in the class aren't in Year 9, so you might have to ask your teacher to give you Year 9 access, okay? And so in the Year 9 curriculum, you can now work through all of Chapter 1, okay, because we did that in the first 2 weeks. You can work through all of Chapter 2, and so we did that in the last 3 lessons, okay? And after today, you'll be able to come into Pythagorean Triples, and then you'll be able to click practice, and you'll be able to start working on questions in Pythagorean Triples, and also in finding the hypotenuse using Pythagoras' theorem. So you can do this practice based on what you're learning here in the Mathspace Academy. Now, if you're a student who hasn't been here in the last 5 lessons, that's okay. If you want, you can watch the recordings that are available. So my classes are always recorded and then uploaded to the Mathspace Academy website later. All right. So feel free to jump into Chapter 1, 2. You should be able to now get through after today the first 2 lessons in Chapter 3. So you can complete these tasks, and this will really help you with your understanding. Okay. Now, it might be that your teacher's already been setting these tasks to you. If so, great, then you don't have to do them. All right. Just a couple of things popping up in the chat box. Great. Okay, excellent. Nothing too exciting there. Okay. Okay, great. Yeah, Yusuf has just asked actually a very good question. I've just jumped into the Q&A. Yusuf Ann has said, hey, Daniel, what happens if you're in a different curriculum? I'm in Year 9 5.3. Okay, does it make a difference? So I'm just looking at the Australian curriculum today, but Yusuf, it sounds like you're looking at the New South Wales curriculum. It's fine, there's no difference. So usually at the Year 9 level, all the states teach a very similar topics, okay? So I know in the Victorian curriculum, we have Chapter 3 is Pythagoras' Theorem, and it's the same 4 lessons, okay? I imagine in the New South Wales curriculum, it could be the same, or actually New South Wales, do you do it in Year 8, Pythagoras' Theorem? Yeah, I can't recall. So whatever curriculum you're in, if you're in a Year 9 curriculum, doesn't matter what state you're in, just work through these chapters that we cover. And sometimes it might be that something doesn't appear. Yeah, so Aaron and Yusuf are confirming that in New South Wales, you do Pythagoras' Theorem in Year 8, right? Okay, so what we're doing today, other states do Pythagoras' Theorem in Year 9, like Victoria, okay? So if you're in the Year 9 curriculum in Mathspace, you might not see Pythagoras' Theorem, okay? You might have to ask for access to the Year 8 curriculum if you want to go back and practice Pythagoras' Theorem, okay? Another example, I know in Victoria, we don't actually have lessons 5 and 6 on factorising. We leave factorising to Year 10 in Victoria. So if there are any Victorian students here today, you might not be able to do lesson 5 and 6. You'll only see the first 4 lessons, and then you'd have to go on to Pythagoras' Theorem, okay? So yeah, if you have a slightly different curriculum, just follow along the best as you can, okay? All right. Yep, just as I mentioned before, classes are recorded, and so after tomorrow, this class will be available, especially if you accidentally drop out or you have to leave early, okay? I'll be asking you questions as usual, and I've been doing that already, and you just write your answers in the chat box, okay? And then if you've got any questions like Yusuf had, which might not be necessarily mathematical, okay, but you've got a question for me, I'll leave some time at the end to answer those questions. Okay, so we're going to make a start on Pythagoras' theorem, okay? And so we're going to be talking today about what the theorem is, Pythagorean triples, and how to identify and calculate the hypotenuse of a right-angled triangle. So this is what we're doing today. Next week, we'll finish by looking at how to calculate the other sides of the triangle using Pythagoras' theorem, and also applications of Pythagoras' theorem, okay? So today is going to be more of a skill building class, okay? And then next week, we'll look at all the real life problems that we can solve using Pythagoras' theorem. So as usual, if you want to do any extra work, extra study on this, because we're only doing this for, you know, an hour this week and an hour next week, Eddie Wu is a great teacher who's got lots of videos, and you can come to our website, wutube.mathspace.co, and all of his videos are there. So you can go find the Australian Year 9 curriculum, jump into Pythagoras' theorem, and you can watch these videos. And so we can see he's got 10 videos on Pythagoras' theorem, okay? So that's for some extra study. So what's Pythagoras? Well, more appropriately, who is Pythagoras? Pythagoras of Samos was an ancient Greek philosopher, okay? So he lived in 570 to 495 BC, approximately, and he is credited as coming up with Pythagoras' theorem, okay? But did he? So historians actually believe that, you know, Pythagoras was not the person who came up with Pythagoras' theorem. Actually, there were previous civilizations like the Babylonians who were proven to have been using Pythagoras' theorem. It's just that Pythagoras, and possibly not even him, but maybe his students, were the one to first kind of, you know, have that formula, but it was really only in the application sense as well. So yeah, Pythagoras actually didn't even really come up with Pythagoras' theorem, but he is, the man is credited. So it's not always in history and mathematics that people who come up with the theorem or named as the theorem, they're not necessarily the ones who first discovered it. It's just that they've got the credit. Okay. Something coming up in the chat box here. Okay, so looking at, yeah, so Aaron, I was just reading Aaron's in the message in the chat box that, yeah, it's written down from, you know, it's in there in ancient Greek books. So we've got that as history, as Pythagoras' theorem. So he's got the credit, but, you know, there's been drawings of like triangles from other civilizations where you can see they've used Pythagoras' theorem, but he gets the name. So before we jump into Pythagoras' theorem, just some revision on a right-angled triangle. So a right-angled triangle has a right angle as one of its interior angles, okay? And so a right angle, remember, is a 90-degree angle, okay? And so the length that is opposite the right angle is always the longest length in a right-angled triangle, and it is called the hypotenuse, okay? So these other side lengths, these ones in black, okay, they have to be shorter than the hypotenuse by definition, okay? So for a right-angled triangle, that length that is opposite the right angle is the longest, and that is called the hypotenuse, okay? So let's go back and look at some questions on this. I keep doing that. Here we go. Right. Okay, so here are some easy questions to start with, okay? So tell me in the chat box, which side of this triangle in the diagram would be the hypotenuse? Would it be length X, Y, or Z? I expect most of you should be able to get this. Yep, so well done. Yes, to Leela, to Brendan. Welcome, guys. Aaron, Yusuf, Remy, Ray. Yeah, well done, guys. The correct answer was Z, okay, or Z if you're not originally from Australia or New Zealand. So Z is how we pronounce it here. And so Z is that hypotenuse. It is the longest length in this triangle's diagram. And I know that because it is opposite the right angle. Okay, so I can submit that and I'll get that answer correct. Very good. Nice, easy one to start with. Now, this next one, okay. So we've got these three towns, Melba, Florey, and Girlang, and they are positioned in this diagram, okay. So which two towns would be the furthest apart, assuming a direct route is taken, okay? So option A, is it Flowery and Melba? Option B, Girlang and Florey, or is option C, Melba and Girlang? Okay. So a few people answering. Let's have a look at some of these answers. Couple of people answering Florey and Melba. Okay, so Florey to Melba. Okay, but remember the right angle triangle, the longest length, okay, is always opposite the right angle. Okay, so if I'm looking opposite the right angle, I am looking at this length. So that means from Florey to Giralong, that must be the longest distance. So when you look at a, if you look at these other lengths, okay, from Florey to Melba or Melba to Giralong, okay, these direct routes, all right, these must be shorter lengths, okay? It might look like in the picture that from Florey to Melba, it's the longest distance, but the hypotenuse, remember, is always the longest length in the right angle triangle. And so the hypotenuse represents that distance from Giralong to Florey. So that means option B is the correct answer. So I had a few people like Aaron, yeah, Brendan, I think Ray. Yep. So some people answered the first one by accident and then they changed their answer. So well done if you managed to change your answer before I told you the answer. The correct answer is option B, from Giralong to Florey. Okay. Okay, going back to wrong button. Going back to my slides. So this is Pythagoras' theorem, okay? So some of you probably know this already, but let me go through it. So we tend to use letters A, B, and C in Pythagoras' theorem. It's very common in a maths class for your teacher to use these three letters, okay? And so C is always that hypotenuse, the longest length of the triangle. And so that formula for Pythagoras' theorem is a squared plus b squared is equal to c squared. And so this is that formula. So how it reads is the square of the hypotenuse is equal to the sum of the squares of the two shortest sides. So that's how you can remember what Pythagoras' theorem is. That's how it's often described. And so it's given here as c squared equals a squared plus b squared. Okay. Now, I will be going through examples of how to use Pythagoras' theorem to calculate the longest side in a right angle triangle in a moment, okay? But also I'm going to look at examples of how to prove that a triangle is a right angle triangle, okay? And so you can do that using this part of Pythagoras' theorem. So if a triangle has three side lengths, A, B, and C, where this relationship is satisfied, c squared equals a squared plus b squared, then you know the triangle has to be a right angle triangle, okay? So for non-right angle triangles, the side lengths do not satisfy this relationship. This relationship only works for right angle triangles, okay? So we're going to use this as well to prove that triangles are right angled. So using this Pythagoras' theorem relationship, okay? And we'll look at triples in a moment, okay? Before we go into the nitty-gritty of Pythagoras, let's do some proofs that actually Pythagoras' theorem is true. Okay, so this is a GeoGebra applet. Okay, and so we've got these squares of area 3 squared, 4 squared, and 5 squared. Remember, the area of a square is length squared, right? So I can, maybe I'll even annotate here. Okay, so the area of a square is always length squared. So then the area of this would be 25 square units. Okay, the area of this squared would be 16 squared units. And then the area of this square would be 9 square units. Okay. And so 16 plus 9, you know, is 25. Okay. Now, and that kind of proves Pythagoras' theorem, but only for this one specific example. Okay. Watch what happens, okay, as I move this slider. So with that square, I can create a parallelogram of area 9 units and a base length of 3, okay, which can then become this rectangle, this green rectangle, which then fits into that square, okay? So if I look at this green rectangle, okay, I know it's got a length of 5 units and some unknown width, okay? But then I know 5 times x has to be 9 square units. So then this width would have to be 9/5, right? Now let's look at the other rectangle, okay? So as this becomes a parallelogram, okay, and then I transform this, so this is a rectangle that still has an area of 16 units, okay? So I can see it's got a length of 5 still, okay? But then I don't know what this width is, okay? But then I know that 5 times y is going to be 16, and then so y is going to be 16 over 5. So now when I add these lengths, x and y, okay, I'm going to get 9/5 plus 16/5, which is equal to 25/5, which is equal to 5. So I've then got that square with a length of 5 and a width of 5. In other words, square of side length 5. So this is just a neat little proof of algebra. It's just a neat little geometric proof for this specific Pythagorean triple. So we'll talk about Pythagorean triples in a moment, but 3, 4, 5 is a known Pythagorean triple, okay? Exiting this, let me just clear my drawings first. Okay, we can also look at this. It's a similar proof, okay? And so for Pythagoras of any known side length, so this isn't just for 3 or 4 and 5, this is for any, okay? What we can do is you can take that area of the smaller rectangle, or sorry, the smaller square, and then you can split up the larger square such that you can move its area into the big square. So this is how the areas of the smaller squares add together to make the area of the larger square. And so that proves this Pythagoras' theorem that a squared plus b squared is equal to c squared. So you have this smaller side length of a and b, and then that hypotenuse of c. And so you've created these squares of area a squared and b squared, and then this is c squared. Okay, so you can see that relationship in action. All right. Okay, let's jump back now and do some more questions on Pythagoras' theorem. Okay, done that one already. Let's do this one. So we can use Pythagoras' theorem, remember, to determine whether a triangle is a right-angled triangle. Okay, so we can say yes, it is, or no, it is not. Okay, and so this Mathspace question is going to take us through it. All right, so if A and B represent the two shorter side lengths, what would be the value of A squared plus B squared? Okay, so use of E, that is correct. We would be writing 10 squared plus 17 squared. Okay, and so 10 squared is 100, and 17 squared, Yusuf has told me is 189.
Oh no! That's okay. Let me work that out. So 17 times 17, 7 7's 49.
7 11. 7 1. Oh, 289. This should be 17 squared. That makes sense. Great. And then, so 100 plus 289 is 389. Thank you for everyone for correcting us. That 17 squared is not 189, it's 289. So then adding those, you get 389. Okay. And then, so in the next question, it asks us to then find the value of C squared. So that longer side length, when you square it, 23 squared, okay, a few people are telling me the answer is 529. Let's double check that. Correct. Very good. So what does that mean? It means, is this a right angle triangle or not? So answer in the chat box for me, please. Thank you, Layla, Yusuf N, Remy, Ray, Yusuf E, well done. Chetna, thank you. So yes, you're all correct. It cannot be a right angle triangle because it does not satisfy Pythagoras' theorem. Okay, A squared plus B squared does not equal C squared in this case. 389 does not equal 529. So that means this triangle, even though the diagram tried to make it look like a right angle triangle, it cannot be a right angle triangle. Okay. Very good. Let's jump to the next question. Okay, so now we're going to be using Pythagoras' theorem. All right, so we have this right angled triangle with shorter side lengths 6 and 8. And so we need to choose the correct equation that satisfies, that's going to help us find the length of the hypotenuse. Okay. So you can either write the equation for me, or you can choose which option from the multiple choice would be correct. All right. So I've only had 2 people answer so far. So is it option A, B, C, or D? What is the formula that is going to give me the correct use of Pythagoras' theorem? So sometimes students can pick this one. Okay. They see some of those squares, but remember the hypotenuse has to be squared as well. It's the hypotenuse squared is equal to the sum of the squares of the other two sides. So the correct answer, okay, and I can see most people are getting this, is option B. Okay, that C squared, the hypotenuse squared, is the sum of the squares of the other two sides. Well, you have to square 6 and 8 and then add them together. Okay, so the correct answer is option B. I can see some people have jumped ahead and solved for what that value is already, which is good. Very good. So yeah, some people are writing the correct answer in the chat box, so I can confirm that. Well done, Aaron. Well done, Yusuf N. Well done, Ray. Correct. So let's go through it now. So then what is going to be the length of the hypotenuse? Okay, so teachers will often show you either one of these two ways. Okay, So when you have c squared equals 6 squared plus 8 squared, some teachers will just tell you to find the squares first. So 36 is 6 squared, 64 is 8 squared. Adding those together, you get 100, all right? So that means c squared is equal to 100. You then take the square root of both sides of the equation, okay? And then when you do that, technically in algebra, this can actually be two values, okay? It can be positive or negative 10, right? Negative 10 times negative 10 is positive 100. But in the context of Pythagoras' theorem, because you're looking at lengths, lengths can only be positive, so we don't worry about this extra part. That's something you should do for algebra later, okay? But for now, c I just know is equal to 10, okay? Using the work of Pythagoras' theorem. So that's one way, pardon me, that's one way you can do this. The other way, okay, what some teachers show you is that you take the square first, okay? So if c squared is equal to 6 squared plus 8 squared, some teachers tell you to do the square root first. Okay, so then you get that c is equal to the square root of 6 squared plus 8 squared, okay? So then that becomes the square root of 36 plus 64, which is the square root of 100. So it's still going to get you the same answer, 10. Okay, it's just a different method, okay? Some teachers will tell you, yeah, Aaron, that's correct. It is basically the same thing. But yeah, some teachers will show you one way, other teachers will show you another way. It's really up to you which way you prefer to do it. I prefer the first way personally, but that's just me. That's how I learned when I was at school. Okay, so I'm not going to bother showing my work in Mathspace. We've got the answer that c has to equal 10. And that is correct. Good, great, very good. Okay, let's look at another example. Let's look at this one. Actually, before we do, now would be a good time to talk about Pythagorean triads, or Pythagorean triples, they're also known as, okay? So, I don't want to do that yet. Ignore that for now. Okay, yes, great. Pythagorean triples. So any whole three numbers, any three whole numbers, I should say, that satisfy this relationship is known as a Pythagorean triple. All right. So we just looked at 6, 8, and 10. Those were three numbers that come together to create a right-angled triangle where 10 is the hypotenuse. All right. And so here's a whole bunch of Pythagorean triples that we know. Okay. And they all satisfy this relationship. Okay. And so the largest number in each of these triples, the largest number is always the hypotenuse. And then the two smaller numbers are the two smaller sides of the triangle. Okay. So I have accidentally revealed my slideshow and where this animation is going. Okay. But really for you guys, you can really make Pythagoras' theorem questions easier, especially when you come to like working on tests and stuff, if you can learn these Pythagorean triples, right? And especially that you create a lot of them just by looking at multiples of smaller ones. All right, so looking at 3, 4, and 5, for example, that's a really common, the most common Pythagorean triple, okay? And it's really easy to remember, 3, 4, and 5. 3 squared plus 4 squared is equal to 5 squared, okay? 9 plus 16 is equal to 25. We saw that in that proof of Pythagoras' theorem that I showed you before. Well, 6, 8, and 10 is the same triple where they've just all been multiplied by 2. So 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. It's the same with 9, 12, and 15. It's that original triple, but all the side lengths have been tripled, okay? It's the same for 12, 16, 20. You can do it for 16, 20, and 25, right? You can do it for 18, 24, and 30, right? You can just multiply, as long as the same number is multiplied on each of those three numbers in the triple, then you can create another Pythagorean triple.
Works the same with 5, 12, and 13. This is another common one, okay? A multiplying each of those side lengths by 2, I'd get 10, 24, and 26. These also satisfy this Pythagoras' theorem, right? As well as 15, 36, and 39, right? So 15 squared plus 36 squared, you can prove it works out to be 39 squared. Okay, 7, 24, and 25 is another Pythagorean triple, and so I can look at multiples of it. So 14, 48, and 50, okay? Or I can do 21, 72, and 75, for an example. 9, 40, and 41 is another one, okay? So then a multiple of 2 would create 18, 80, and 82. Looking at 11, 60, and 61, okay? That one's not often taught, but yes, of course, it satisfies Pythagoras' theorem, so would then all of the side lengths double, 22, 120, and 122, okay? So I can use Pythagorean triples now, okay, to answer Pythagoras theorem questions quickly without having to do any work, okay? So if I didn't know Pythagorean triples, I would be forced to work this out from scratch. I would be forced to go, okay, c squared is 9 squared plus 40 squared. I'd have to evaluate the squares. I'd have to add them together and then take the square root. But because I know 9, 40, and 41 is a Pythagorean triple, I could straight away answer this question. I can say C, I've got my numbers 9 and 40 as the shorter side, so C has to equal 41. And so that's the correct answer. So once you learn a couple of those Pythagorean triples and even multiples of those triples, solving Pythagoras theorem questions can be quicker, okay? But only when you know you have whole numbers as the answers, okay? Yep, so just looking at the chat box, sorry, I didn't really give everyone time to solve that. Yeah, so yeah, everyone was getting the answer there, 41. So maybe you worked that out yourself, or maybe you remembered from my slides that 90, 40, and 41 was a Pythagorean triple. Okay, great. Let's go to the next question. Where's my mouse gone? There it is. Okay. I'm in full screen mode, that's why. Okay, great. Next question. So not always you're going to have whole numbers as answers, okay? Sometimes when you find the hypotenuse, you're not going to get, you know, an integer answer. Sometimes you're going to get decimals or surds in this case. So this particular question, okay, and this is one reason why we learn surds, okay? So we can find the exact solution to a question like this. So now we need to find the length of the hypotenuse using, in this case, Pythagoras' theorem. And so I can see a few people, looks like they're getting the answer. Ray, yeah, a few people, yep, Aaron, that's right. So yeah, a few people writing the answer correctly in the chat box, okay? So let's just go to here. Just be careful how you show your work as well, guys. Some people in the chat box, I can see you getting the answer right, but when you write c squared is equal to the square root of 106, that's actually incorrect as a mathematical statement. So do be careful in the way you present your work as well, okay? So remember, Pythagoras' theorem would be that the square of the hypotenuse, which we don't know, is going to be the sum of the squares of the other two sides. So 5 squared plus 9 squared. So some people in the chat box, I can see wrote 25 plus 81, which is equal 106. So that means C equals the square root of 106 when we take the square root of both sides of the equation, okay? Now, you can't evaluate the square root of 106. Sometimes you can simplify these surds, okay? But this is an example of a surd that cannot be simplified, all right? So this answer as a surd is just the square root of 106. So well done for some of you guys who got that answer correct in the chat box before I even showed any work, okay? And I'm not particularly surprised, especially if there are some students here from New South Wales who've covered this already in year 8, okay? Do be careful, okay? I have seen 1 or 2 people have presented their answer in decimal form, okay? And so you'd actually lose a mark because you need to read the instruction. You're giving the answer as a surd, okay? So I have to leave it as the square root of 106. If I then go say it's equal to 10 point whatever, I haven't read the instruction correctly. So I might lose a mark from my teacher if I don't give the answer in the way that the question instructs. Okay. Moving on to the next question. So this is an example where now, rather than answering as a surd, we're asked to give the answer to 2 decimal places. Okay. So using Pythagoras' theorem, the square of the hypotenuse is going to be the sum of the squares of the other 2 sides. So 4 squared and 15 squared evaluated together. A common mistake for students, they think 4 squared and 15 squared is the same as 4 plus 15 all squared. Okay, be careful not to do that. That's wrong. Okay, remember, if I have 4 plus 15 squared, okay, that's going to be the same as 4 squared plus 2 times 4 plus 15 plus 15 squared. Okay, there's this additional part that needs to be added. I'm using that formula that we covered at the start of the class. So this is an incorrect factorization. All right, but it is a common mistake that students make at the beginning. So I did want to point it out. Okay, so what we're supposed to do is evaluate the squares. So I get 16 plus 225, 15 squared is 225. Adding 16 to it, I'm going to get an answer of 241. So then when I take the square root of both sides, C will equal the square root of 241. Now, when you're asked to give the answer to 2 decimal places, this is when you need your calculator. Okay, so if I pull up my basic computer calculator, taking the square root of 241, where is that square root button gone? I think I pressed the second feature. Yep. So taking the square root of that, I get this answer of 15.52. Okay. So if you write C equals 15.52, that is the correct answer. And I don't need to worry about units of measurement, okay, because I haven't been given any. All right. So you could, technically, because it is a length, you could write units next to your answer. Okay, it is 15.52 units of length, all right, and you don't know what that unit is, okay? But if these answers had meters next to them, okay, you would have to write meters next to your answer, okay? And so we'll look at some of those applications next week in class, okay? All right, let's look at a couple more questions and then we can finish for today, okay? So remember, okay, I know that it's option B that is going to satisfy this, but rather than having to do the work, I could answer this straight away. Can anyone answer this straight away? If I now look at part B, thank you for those of you who selected option B as the correct answer. For part B, what's my answer for C? Straight away without having to do any Pythagoras work, I challenge you. Okay, so Yusuf N, I can see you've got that correct. All right. So the challenge is to be able to do this without any working out whatsoever. If you need to, you can do the working out, okay? So you can do C squared is equal to 12 squared plus 16 squared, which would be 144 plus 256. These numbers add to 400. Okay, so if C squared is 400, you can take the square root of both sides, okay, to get the C is equal to 20, okay? And so, yes, a few people in the chat box are pointing out that this is a Pythagorean triple, or otherwise known as a Pythagorean triad, okay? So remember, basic 3, 4, and 5 is a Pythagorean triad, okay? And so 3 times 4 gives 12, 4 times 4 gives 16. So I can, from that triad, okay, multiply both these numbers by 4. So then that 5, I can just multiply by 4. Okay, so you could write in your working, C just has to be 5 times 4. Okay, and so that will be 20. And so, yeah, knowing what you know about Pythagorean triples, there's no need to do all that equation work, okay? Because you know 12, 16, and 20 is a multiple of 3, 4, and 5. If you're considering a right-angled triangle, so it's very important, you do have to know it is a right-angled triangle, okay? You have to see that right angle appear, okay? If you're not given that information, you can't assume it satisfies that relationship. But because we were given that relationship in this question, we're told the angle's right, we're told the triangle's right angled, okay? We know that the missing length is the hypotenuse, okay? And these, we can just use that Pythagorean triple, 3, 4, 5, multiplying all the side lengths by 4, okay? To find that missing side length of 20, okay? Keep in mind, and this is something that we'll do later in the year when we talk about similarity of triangles, okay? I'm jumping ahead by a couple of weeks, okay? But when you look at a triangle, all right, and might have side lengths 3, 4, and 5, you can use what's called a scale factor. So it's like zooming in, for example, or zooming out. And so you do it by a factor of, in this case, 4. Okay, so what I'm doing then is I am multiplying all my side lengths by 4. Okay, so I get 12, 16, and 20. Okay, and so these triangles, okay, actually, when we start talking about congruent triangles and similar triangles later in the year, these angles, which we'll also talk about later in the year, finding these angles using trigonometry, these angles in similar triangles are actually the same, okay? So these 3 angles, 1, 2, and 3, match these 3 angles, 1, 2, and 3. The only difference is those side lengths have been multiplied. So that's what we mean by a scale factor, okay? Where those side lengths are all multiplied by the same number. So it's a similar triangle because those angles stay the same. And so because those angles stay the same, it's still a right angle triangle and it's still going to follow Pythagoras' theorem. All right. So that's jumping a little ahead. Remember this when we talk about similar triangles later in the year, later in the term, I should say. Okay. Looking at this triangle, length of the unknown, side C, write each step of working as an equation. Okay, so you've got side lengths 7, 24, and C. Okay, so what is the answer? Yeah, so someone's actually identified the answer straight away. A few people have, okay? So again, this is a Pythagorean triple, all right? So there's actually a known Pythagorean triple of 7, 24, and 25. So this is just another example of using that Pythagorean triple to find that the hypotenuse is equal to 25 without having to do any work at all. Okay, I think that is it. Okay, all right, I'll do this one last question and then I'll give you my challenge question that I want you to work on across the week. Okay, so here we're told a rectangle has side lengths 6 and 8. Find the length of the diagonals of this rectangle. Okay, so suddenly we're not talking about triangles, we're talking about rectangles. What gives? Okay, so draw the rectangle. All right, we know it's got a width of 6, a length of 8. Okay, and so this is a rectangle. And so the diagonal of a quadrilateral, okay, you're going from one corner to the other. Well, guess what? That creates 2 right-angled triangles, okay? So I can just consider this right-angled triangle, okay, which has, I know it must have that same height, 6, and a base length of 8. Okay, and then so I can define that length of the diagonal, maybe as d, for example. So d squared must then equal 6 squared plus 8 squared. Okay, so this is just an application of Pythagoras' theorem. Now, note in Mathspace here, I have to define the length of the diagonal and it's not squared, okay? So if I was to write my working, I would have to write the square root of 6 squared plus 8 squared, okay? Or you can do your work on a piece of paper and then just put in the answer here at the end, okay? And so I'm guessing the chat box is blowing up here. Some people are coming up with the answer. Yes, so a few people, Yusuf N, Remy, Ray, well done. A few more people above them. Yeah, Yusuf E, identifying that diagonal length must be 10, okay? So again, you're looking at the square root of 100, which is 10, or you can use that Pythagorean triple 6, 8, and 10, being a multiple of 3, 4, and 5, okay? Great. All right, so we're going to finish, but let me pose you first a challenge question that I want you guys to try and work on between now and next week, okay? So here it is. Here we go. Challenge question. Let k be a constant, okay? And now that constant's actually what's known as a scale factor in similar triangles, but more on that another day. Let's just consider k to be a constant number. It can be any number, okay? It can be any real number. It doesn't have to be a whole number. It could be a real number, right? And a, b, and c, let it be a known Pythagorean triple, okay? So we know it satisfies Pythagoras' theorem. Prove using algebra only that for any letters K, A, B, and C, that KA, KB, and KC must also be a Pythagorean triple. Okay? So we have seen this as examples with triples 3, 4, 5, 7, 24, 25, 9, 40, 41, 5, 12, and 13. We've seen examples of multiples actually satisfying Pythagoras' theorem still, but I haven't shown you definitively why, okay? And so I would like you to try do that between now and next week, okay? So you can't just show me 3, 4, and 5 works for 6, 8, and 10 and then go, yep, it works, right? Because you're only technically showing me one example. You're not mathematically using algebra to prove that it's going to work for any number you substitute for K, A, B, and C, all right? So I'd like you to try that, and I will reveal the answer at the beginning of next week's class, okay? So I'll just give you 30 more seconds just to maybe write this down in your books in case you want to try it between now and next week, okay? Prove using algebra that if you know A, B, and C is a Pythagorean triple, prove that KA, KB, and KC will also be a Pythagorean triple. All right? Okay. Actually, I'll leave that on the screen. And while I do that, I will look at the chat box and I'll look at the Q&A. Okay. That must have just been... so someone asked, should we copy them all down, the known Pythagorean triples? Okay, I think that's a great idea. I think you should, in your book, you can just have 4 Pythagorean triples. Okay, if you just memorize 4 of them, okay, I'll write them in the chat box now, okay? If you memorize these 4 Pythagorean triples, okay, if you memorize 3, 4, and 5, you memorize 5, 12, and 13, if you memorize 7, 24, and 25, okay, and what was the other one? There was 9, 40, and 41. Okay, even if you just memorize the first 2, okay, you'll find that a lot of Pythagoras questions that you have to answer are usually multiples of just the first 2, okay? But then you could use, you could then use, you could use the other two as well for harder examples, okay? So those ones that I've just written in the, I've actually, sorry, I just wrote them just array. My apologies, hold on. All attendees, I want to write those 4, there we go. There they are. Sorry, everyone. So yes, those are the 4 Pythagorean triples that you could just go ahead and memorize, okay? And that will, yeah, really help you. It's a great trick. Helps you then solve Pythagoras questions quicker. Not always, because as we saw in today's work, you know, sometimes you have decimal answers, sometimes you have surd answers. So then they don't particularly work for those, okay? But yeah, if you memorize a couple of these triples, it will make the work easier and quicker. All right, great. I don't see any other questions. Someone anonymous has asked, are you looking for the answer as a formula? Yeah, I am. You need to do algebraic formula work in that challenge question, okay, in order to do it correctly. Okay. When will we do congruency? Good question, Yusuf N. Let me double check. Okay, so scale and similarity is actually the next topic that we do after Pythagoras' theorem. So next week we'll finish Pythagoras' theorem. So the following week, so on the 28th of May, in that lesson, lesson 8, we will start on scale and similarity. Okay, and I'll talk about scale factors. Okay, and similar triangle tests. So that's the work we do in chapter 4. I then, after that, I think how I've planned the term is I'll actually skip then to trigonometry, and we'll start trigonometry because you can expand on similar triangles using trigonometry, okay? And then I'll come back to equations and graphs later in the end of the term, okay? All right, I think that's about all we have time for. Anonymous, what was the max people that I had personally had at a Mathspace Academy session? I think I had about 30 people in that first lesson, but there were a lot of teachers who attended. It was the school holidays and they wanted to have a look and see what was going on. I'd love to have more people here. So yeah, please feel free to invite your friends. I suspect though now that students will be coming back to school, okay, you all have to be back in the classroom by Tuesday the 9th of June. That's just for Victorian teachers. Other states, you're going back to school sooner, okay? It might be a bit harder for you to attend these live sessions if you've got other classes. So yeah, we'll have to evaluate, see if we still do this into term 3 and beyond. Yeah, I've answered that question. Here we go. A random question. If 1 to the power of 0 is 1 and 0 to the power of 1 is 0, what is 0 to the power of 0? Great question, Anonymous. We actually covered this in the indices class, I think, at the beginning of the year, beginning of the term, or maybe it was in the school holidays. So 0 to the power of 0 actually doesn't have an answer, right? It's not 1 and it's not 0, okay? It's an undefined number. Okay. All right. So that's all we got time for. I better shoot off, guys. So thanks very much for coming to class again. And yeah, I'll see you all next week. Okay. All right. Take care, everyone. And I'll see you all later. You can now, in Mathspace, if you have access to it, you can now do these first 2 lessons in Pythagoras' theorem. Okay. So if you can get through all those questions, if you can master those subtopics, you'll really, solidify what we did today. And if you've covered this in class already, or if you've done it in year 8 already, great, you can put it away. What's done is done. Okay. And if you haven't done it in class yet, you'll be really super prepared when your teacher covers it. Okay. And you could even ask them for some more challenging work to do. All right. I'm going to finish off there, guys. Thanks very much. I'll see you all next week.